Okay, so I want to do a couple of problems that uh, use these directions. So these are the directions we've been doing for most of the standard problems now for the past week or so. But it just says show whether the series converges or diverges. And I'm going to put 3 on the screen, and I want to work through them relatively quickly. So on the first problem, we're going to do the sum k equals, let's say, 3 to infinity of 5k plus 7 over 6k to the third, and we'll say minus k plus 1. And then number 2 is going to be the sum k equals 2 to infinity of, we'll do, excuse me, 3 square root of k plus 5 over 7k plus 6. And then number 3, I'm going to put it down here just if you want to write it down. So k equals 1 to infinity of, let's do 3k minus 6 over the square root of 16k squared plus 1. And so, okay, so I want to talk about these 3 kind of together. My bad. And you know what? I want all of these to be alternating, so I apologize for that. So we've done comparison tests with these, but let's change it real quick. My bad. Negative 1 to the k times what we have. So negative 1 to the k times 5k plus 7 over this, and then negative 1 to the k times 3 squared of k plus 5. And it could be like negative 1 to the k plus 1 times 3 squared of k plus 5. And then this last one, we'll just make it, we'll get rid of the minus 6. It doesn't really matter much. So negative 1 to the k times 3k. Okay, my bad. So I do want to talk about the alternating versions to these, which is what we were talking about yesterday. So in these cases, I want to go through them relatively quickly because we did go through the rationale of these yesterday. We should start by considering the absolute value. So we kind of come over here and we say, okay, consider the sum of the absolute value of AK, which is then 5k, the sum 5k plus 7 over 6k to the third minus k plus 1. And then that's a series where the terms are all positive. And so we compare that to the series 5k over 6k to the third, where we're taking the largest term on top and largest term on bottom. And then we can factor the 5, 6 out, and we get 1 over k squared. That series now converges. And the reason why is because it's a p series where p is 1, I'm sorry, where p is 2, which is bigger than 1, and we might say it's a constant multiple of a p series where p is 2, which is greater than 1. Does that make sense to everybody? I know I'm going kind of quick through this. Any questions so far on this? Okay, and my bad, I did not have chat pulled up, but no questions in the chat either. So, okay, so then now we're going to go back. And all right, so we've proven that the one on the far right converges. Now we're going to look at the one in the middle. And it's also going to converge by one of the 2 comparison tests. And so because the one on the right converges, we would like this to be smaller than that. And when I say we would like it to be smaller, I mean in order to use the direct comparison. So like this one levels off. So if this is smaller than this, then this one would also have to level off, could not go to infinity. But in this case, this one is larger because the top is larger and the bottom is smaller. That means we need to use limit comparison test, which is not much harder. So we just say, okay, well, 5k plus 7 over 6k to the third minus k plus 1 is greater than 0. And 5k over 6k to the third is greater than 0. And then we take the limit as k approaches infinity of one of them divided by the other. So 5k plus 7 over 6k to the third minus k plus 1 times the reciprocal, so technically divided by that. So times the reciprocal of the other one, so 6k to the third over 5k. That's equal to the limit as k approaches infinity of 30k to the fourth over 30k to the fourth, which is 1, and that's bigger than 0. So this middle series converges by limit comparison test. Okay. Questions to there? We're not done for sure, but does everybody follow that? All right, so we've kind of done two separate proofs. We've done a quick proof that this one converges because it's a p-series. We've done a quick proof that this one converges, a less quick proof, that this one converges by the limit comparison test. We haven't actually said anything about the original series. And so what do we do here? How do we...
Since its absolute value converges, the original series converges by the absolute conversion.
Perfect. So you come in and say, okay, so since the sum of the absolute value converges, this original series, and what we said yesterday is I will assume that when you write AK, you mean the original series, unless within your explanation you tell me AK is supposed to represent something else. So we're going to operate under the convention that AK represents the original series. So absolute value is this one. The original series is the sum AK. And so we're and it converges absolutely. And the name of the theorem that allows you to make that conclusion is the absolute convergence theorem. And so it kind of sounds like you're repeating yourself, but the answer is that this converges absolutely, and it converges absolutely by the absolute convergence theorem. And I probably should have made the direction say, show whether it converges conditionally, converges absolutely, or diverges. And I'm not going to take the time to change that, but we're going to show that it converges absolutely here. Does that make sense? Any questions so far? Okay, and so I want to go to the second one real quick. And so we're going to come over here and say, okay, we'll consider, we start it the same way. So consider the sum of the absolute value of AK. -1 to the k plus 1 still alternates, right? So -1, if I put in, say, 2 for k, then I get 3 up here. And if I put in 3, I get 4, and then 4, I get 5. So it still goes even, odd. And so then that means that when you do -1 to those, it alternates +1, -1. So it looks somehow harder, but it's not. The absolute value of that part is 1. Everything else is positive. So the absolute value of this is the sum 3 square root k plus 5 over 7k plus 6. And then we're going to in turn compare that to 3 square root k over 7k. That simplifies to 3/7 times the sum 1 over k to the 1/2, because you've got k to the 1/2 on top and k to the first on bottom. Let me make that a little bit clearer. But that is k to the 1/2 on bottom. I think we can read that better now. All right. And so then the series over here diverges. Because it's a constant multiple of a p-series where p is equal to 1/2, which is less than 1. And so p-series where p is less than 1, those diverge. So now we're going to go back, and this middle series is going to do the same thing that one does. So this, in this case, this diverges, so it goes to infinity. So like the graph we think of as going way up. If we could prove this is larger than that, then this would have to diverge by direct comparison. That would be a hard argument to make because the bottom is larger. So you've got 7k plus 6 in the bottom. The top's bigger too, and so maybe we could prove that. I think probably not. Here, I think this is probably not always larger than that. In either case, because it's not clear, then we should just default to limit comparison test. So we should go and say, okay, well, 3 square root of k plus 5 over 7k plus 6, that's positive. And then 3 square root of k over 7k, that's positive. And now the limit as k approaches infinity of 3 square root k plus 5 over 7k plus 6 times the reciprocal of the one on the right. If I distribute and take the largest terms on top and largest terms on bottom, I get 21k square root k over 21k square root k. Well, that limit is 1, which is greater than 0. And so then the sum of the absolute value of AK diverges by limit comparison test. We're not done, but are there any questions to here? Go ahead.
If on the previous problem, if since 1 is greater than 0,
Yep.
then the limit converges. Why is it different in this problem?
So what the limit comparison test says is that if you get any number here that is greater than 0, that this series behaves the same way this series does. So if this one converges, good question. If this converges, this also converges. If this diverges, this also diverges. And I'm purposely doing one where they're both limit comparisons so that somebody would ask that question. So thanks. But do we understand what I'm saying?
Yeah. Okay.
Awesome.
I think somebody's already asked this question, but I just want to make sure.
That's okay. And it may come up again. So keep asking. What is it?
Can you always use the limit test?
Almost always. So on the standard problems where it's like all power functions like this, or if it's all exponential functions, then yes.
Okay.
Because it's not like these limits aren't that hard. You know what I mean? Mm-hmm. And so like it might be easier to just do this limit than it is to decide whether this is bigger or smaller. And not that that's that hard, but it's easy to get backward. You know what I mean?
Yeah.
So like here you want it to be smaller, here you want it to be bigger, and there's a lot of little places to mess up. So like most of the time, yeah, you can. There are some examples where if you were to do the limit comparison, the limit would not exist. And a couple of those examples are the ones we were doing at the end of the lecture the other day that involved like sine and cosine. And so like you had a sine on the top, a sine on the bottom. So you do need to understand the idea of the direct comparison for those. But on these problems, you could default to limit comparison every time. Does that answer the question?
Yes, thank you.
Yeah. And if you're asking a question that comes up again, that's normal for this stuff. So like when you're working a problem, you're going to think, oh, well, what if this happens instead? And we probably have talked about it before, but that's completely fine. You should be asking that again, and you should be thinking about that again. So don't feel bad if you guys think I've answered a question, ask it. I want you guys thinking about that stuff. All right, other questions? Everybody good? Okay. So here, this one converged, this one converged. So then, okay, this converged absolutely by the absolute convergence theorem. What happens in this case? So this diverges and the absolute value diverges. What does that tell you about the original? It actually doesn't tell you much. It doesn't tell you whether it converges or diverges, but it tells you that it does not converge absolutely. And so like I said, I should have included that in the instructions, but this can't converge absolutely because its absolute value diverges. But probably this still converges. And we're going to talk more about probably this still converges in a minute. But this converges by the alternating series test. And so we're going to go through that quickly. And I'm actually going to skip a little bit of detail here. But we're going to say, okay, BK is the non-alternating part. And we're going to show 3 conditions for the alternating series test. The conditions are all about BK, meaning the non-alternating part of the series. So the 3 conditions you show are about BK, but they show that the sum of AK converges. So if these 3 things are true, then AK converges. So the first thing is that BK is positive. Well, that is pretty clear because everything here is positive. And so you don't need to give much explanation, but you do need to be right about that. And then the second condition is the limit as K approaches infinity of BK is 0. And so here. Takes a couple steps, and maybe you could just look at that and know that it's 0. I'm not concerned with you showing me every step here. If you can look at that and realize, okay, the biggest thing on top is smaller than the biggest thing on bottom, and so I know it's going to 0, fair enough. But the limit of that is 0. And the third thing is that BK is decreasing, and I'm going to not show the details of that here. Yesterday, we showed a couple simple examples of that. Here, probably the best call is to say let f of x equal 3 square root of x plus 5 over 7x plus 6, and take the derivative of that and prove that it's negative. And so if the derivative is negative, that means the slope's negative, but this is in fact decreasing. And like I said, we'll just, for time, I don't want to focus on the detail of how to show that. But you would take the derivative of this using the quotient rule, and you would be able to tell, okay, well, the bottom is squared, which is positive, the top is negative, and so then that means the whole thing is negative. So then the function is decreasing, which means the sequence is decreasing. Okay, those three things mean then that the original series converges, but it converges conditionally by the alternating series test, which I'm going to abbreviate today AST, but that stands for alternating series test. And so now, if you back up and look at these two problems, the format of these two problems is almost the same. Okay, and so when you have alternating series that meet kind of the standard mold, like meaning that, okay, you have the -1 to the k or -1 to whatever that makes it alternating, and then the rest of it is all power functions like these. Or it could be they're all exponential functions like 5 to the k or 3 to the k. And then here, you know, instead of k to the 1/2 to the k or 7 to the k. So if you have it where you don't have this mixture of functions, if it's all exponential or if it's all power functions, with the exception of the -1 to the k part, then they follow this mold where you start by taking the absolute value. And then you go over and you compare that. And this is a P series because it was all power functions at this stage. If these were all exponential functions, what would happen here? So if it was like 5 to the k and like 6 to the k instead of 5k and 6k cubed, if it was 5 to the k and 6 to the k, what would happen over here? Instead of a P series, what would you get? What do you guys think? So it was 5 to the k, 6 to the k. What would happen here?
Geometric.
Yeah, it'd be a geometric series, which would be like 5, 6 to the k. And so over here, you're going to have either a P series or a geometric series. Does that make sense to everybody? And then we're going to be able to determine using that whether this converges or diverges. The one in the middle is going to do the same thing that the one on the right does. So if this converges, this middle one converges. If this diverges, the middle one diverges. That's going to be either by the limit or direct comparison. And like that guy was asking a couple minutes ago, you could probably just use limit comparison every time. But regardless, the conclusion here is the same as the conclusion over here. Does that make sense? Now, if this converges, then the one on the left is easy. It converges absolutely, automatically by the absolute convergence theorem. You could choose to do alternating series test, but you don't need to because we already know this converges. So then this converges absolutely. So we get the pattern that, okay, this converges, and then we go back, this converges, and we go back, and this converges absolutely, converges still, but we say converges absolutely because the absolute value converges. The red is representing the order that we actually work it in. So like we start finding this middle series, then we find the series on the right, but we actually prove what happens from right to left. So we prove, okay, this converges, so this converges absolutely. Does that make sense? Okay, over here, when you get over here, this one diverged. Well, then we go back and one of the comparison tests proves that this one diverges. And then what we haven't really said yet is that every example we've seen, you get back over here and it converges conditionally by the alternating series test. You can't use the absolute convergence theorem because the absolute value did not converge, but the alternating series test is held. So let's think about what happens with these three conditions. So if BK is not positive, so if BK, like, if it's always negative, you could factor a negative one out and then BK, you would just like get rid of that negative. You would make it part of the alternating part. Does that make sense? So like you'd make BK the positive version of it. So that's a trivial thing. But if BK switches back and forth, then chances are this is not actually alternating. Does that make sense? So on these standard problems, when you get rid of this negative one of the K, BK is going to be positive. If not, it's not really an alternating series. The second one, that the limit of BK is 0, what would happen if that weren't true? What if the limit of this sequence
Would it
weren't
diverge?
true? The whole series would diverge. Why?
Because it doesn't meet the conditions.
Not that reason. It doesn't meet the conditions, but why, if the limit of this sequence is not 0, why does the series diverge? Different reason. It's okay.
Oh, because then you're adding a number
yeah.
continuously.
And what's that test called? So if the sequence doesn't go to 0, then say it again. Sorry.
Said it's on the tip of my tongue.
Yes. All right. Somebody else know? So if the sequence doesn't go to 0, then the series diverges. That's something we learned a while ago. What is that?
K series.
The K-term test or the
K-term.
test for divergence. You were good. So it's the K-term test or the test for divergence. So if this weren't true, we shouldn't have been doing any of this because we should have been doing the K-term test and just say it's divergent from that. So we should know beforehand that this is going to be true before we get to any of this stuff. And then the third condition is going to be true on the standard examples. And we'll talk a little bit more about that in a minute. But the idea is then, okay, real quick, let's work this problem. So this problem, if we got over here, you would have K over the square root of K squared, which is K over K, and that's weird. That's 1. So this problem, the way we work it out is we say, okay, the limit as K approaches infinity, and we'll do the absolute value of AK. So we get a limit of 3/4. And on the K-term test, what that means is you're doing, okay, 3/4 plus 3/4 plus 3/4 plus 3/4 forever. That means it goes to infinity. Now, if it's alternating, you're bouncing from like 3/4 plus negative 3/4 plus 3/4 plus negative 3/4, which means the partial sums are bouncing. And so either way, it diverges. So we say, because this is not 0, this series diverges by the K-term test, or we could call that the test for divergence. Does that make sense to everybody? Now, the point of this discussion is we should know everything that's going to happen as soon as we're able to determine what this far right series is. And you don't need to write this to determine what this P series is going to be. If you look at the original problem, how could I have known just looking at this that I was going to get 1 over K squared over here? How could you
initially describe the biggest K term from the top and bottom?
Exactly. You're looking at the biggest thing on top, biggest thing on bottom, ignoring the negative 1 to the K. So you've got 5K over 6K to the third. The 5, 6 isn't going to matter. It's going to factor out anyway. And so K over K to the third is 1 over K squared. So that meant I knew ahead of time this was going to converge, which meant the middle one was going to converge and the one on the left was going to converge absolutely. Does everybody see that? So these are the prime examples of nothing that you're really writing is being used to determine an answer. We should know the answer ahead of time. We should know this format before you start writing anything. If you need to write it to figure out what this is going to be, fine. But as soon as you get this P series, we should know all of the format of the proof. None of this is actually being used to determine an answer. It's being used to prove that you are correct. Does that make sense? Everybody clear what I'm talking about? So, okay, on this one, how could I have known it was going to be 1 over k to the 1/2? What would I pick out of this to look at that and know it was going to be 1 over k to the 1/2 over here? What's the important part? What do you guys think?
3 square root of k and 7k.
Yeah, 3 squared of k and 7k, and particularly square root of k over k. Well, we know that's 1 over square root of k, or 1 over k to the 1/2. That meant I knew this was going to diverge, which meant the middle one was going to diverge. And then this isn't k-term test. So then if it's not k-term test, it's going to converge by the alternating series test. And so it converged conditionally. So we knew the answer before we, or I knew the answer before we started, and I want you guys to get to that point. Does that make sense? Down here, how do we know it's k-term test? By looking at it. Like if we were to do this format, what would happen over here is we would get k over the square root of k squared. Well, that's k over k, which is 1, which is not really a P series, right? I guess technically you could talk about it as a P series, but it's really not in the normal format. And so that in that case, we knew that something weird is happening, and that's when we're going to use the k-term test. We're going to take the limit of the sequence, or at least the limit of the absolute value of the sequence, and get something other than 0. Does everybody follow that idea? Real important. So please ask if any of this is unclear. Okay, so the idea is that these two parts of the alternating series test are going to be true on the standard problems. If this part is not true, if the second part's not true, then it's k-term test. Now, if these two parts are true, so what I want to talk about is decreasing. So think about if you have a positive sequence and the limit of the sequence is 0, then the graph should look like that. Does that make sense? So if all the terms are positive and it approaches 0, this is the most obvious graph for something like that. Everybody see why? It'd be a bunch of dots, but it's easier to think of as a smooth curve. You guys get what I mean? Now, so what I'm trying to get at is if these two things are true, this is almost always automatically true. It's almost always automatically decreasing. If it weren't, it would be something really weird where it's like bouncing randomly toward 0. And so then, okay, it's not decreasing. If something like that happens, then you might have one where this diverged, and then this doesn't converge, but it's not k-term test. It still goes to 0. So maybe we could come up with something real weird like that, but not when it's the standard problems. When you have ones where it's all power functions and all exponential functions, this is not going to happen. You're going to need sine or cosine or something weird to make that happen. Does everybody get what I mean by that? So the idea is if these two diverge, then on normal problems, this is going to converge anyway, unless it's k-term test. Everybody clear? Okay, so 3 cases on what we will consider normal or straightforward alternating series test problems. These are the 3 cases. They're normally in 3 parts. If you get the one on the right and it converges, automatically the middle one converges and the original one converges absolutely by the absolute convergence theorem. So we've got P series, a comparison test, and then absolute convergence theorem. If the one on the right diverges, then okay, that diverges, the middle one diverges, and the one on the left converges conditionally by the alternating series test, unless the reason it diverged was k-term test, and that's just a completely separate thing. Okay, any questions on that?
Yeah.
Yeah, go ahead.
For a test question,
Yeah.
what percentage of material for any of these given problems do you want to be shown?
Okay, that's a really good question. So I'm actually gonna pull up an old exam. You guys are in a little bit different situation because you're taking an online test. So a little bit of this is undetermined as far as what you are gonna have to do. But I'm gonna show you the way tests have looked in the past from me on this. And then as I know more about how your electronic test will look, I will be open about that. I just genuinely do not know yet about the open test, or the online test.
It'd be quite interesting to see how you would make something like this multiple choice.
Well, okay, let's talk about that. But let's look at. There's a good chance there's going to be a written part of this, but I just don't know that yet. But let's look at if we were going to written test in a normal classroom situation. Here is what. Give me 1 second, and I'll pull it up. Here is what one of my old exams looks like on this. And you guys have access to these old exams. If you go into the shared drive and old exams and then Doug's exams. And so, okay, spring 2018, I assume was not like a weird semester. Let me look at that and see. My exams, the ones that say Doug's exams, are older because the exams became departmentalized and I was not coordinating the class for a year or so, and now I am coordinating class, so I'm writing the exams. But the exams last year were written by somebody other than me, so that's why if you look at the ones that say Doug's exams are a little bit older. Okay, so this semester in spring 2018. And let me share this. Spring 2018, it was on exam 4. We had 4 exams that semester, so this stuff was on exam 4. And so here is what it looked like. So there were, and this is what I normally do, and this is what will translate well to an online test, I think. So on this first part, there were 6 problems, sometimes 7 or 8, that were worth 6 points each. And you had to just give the answer, and you had to list the test that you would use. So you did not have to show any detail. You had to say either converge absolutely, converge conditionally, or diverge in the conclusion blank. And then you had to say something like P series, comparison test, and alternating series test. Or P series, this one's not alternating. So like this one would converge absolutely. This would be P series and comparison test. And on these, you did not have to make a distinction between whether it's limit or direct comparison. You only had to do that on the ones where you had to show all your work. Does that answer some of your question? And does that make sense to everybody? This is actually the next type of problem we're going to do where we don't show all the work. That's the next set I want to do. And maybe we'll actually just pull up this page and do it here in a second. I want to do a bunch of alternating ones. So we'll practice this before the exam. But on that page, you had to show no details. Okay, so you had to say what the answer was, and you had to list the conclusion. But it wasn't like if you did show some detail, then you lost points. Like if you wanted to jot down what the P series is, you could of course do that. But you had to list the names of the tests, and you had to list the answer. And then there were fewer questions. Prove whether the series converges absolutely, converges conditionally, or diverges. Show all conditions. If it says that, then you would show everything that I'm writing on the screen. Does that make sense to everybody? I don't know who was asking that. Does that make sense to you in particular? So somebody saw me.
Yeah.
Okay. So like when we did it on that semester, it looks like there were 3 where you had to show all the details, but it looks like we had gotten further. So anyway, this is the part I'm not sure how that's going to go with an online test. I would anticipate a lot of this, and that will go well on a WebAssign. So you'll have like the option. There'll probably be a multiple choice: converge absolutely, converge conditionally, or diverge. And then there will probably be some way to indicate what tests you should use. That I just don't know how that's going to look yet. But the electronic ones would be like this. And then if there's a written portion, there would be ones where you do have to show all of the conditions. Does that make sense?
And that'd be something more like where we upload the work on CrowdMark and you grade it
100%. I just genuinely, because it's 2 weeks off, I haven't even thought about it. And I'm about to take a weekend off and like not even look at email, which I'm excited about. So I'll know more next week at the end of the week, and then definitely the week after. But it's not like I'm not telling you. I just genuinely don't know how it's going to look.
Yeah, no, that makes sense.
Yeah, no, it's fine. I'm trying to be as open as possible. But do look at these old exams, because the plan is to make it as much like this as possible, but be able to manage it with an online exam. Okay. All right. Any other questions so far? Is this making sense, you guys? Okay. So what I want to do is this type of problem. So I'm actually glad you asked that. That's what we wanted to do next, is rather than going through the all of the details of the proof, I'm going to put several on the screen. And what I want you to do is state whether it converges absolutely, converges conditionally, or diverges, and then state the test that you would use. And actually, let me show you real quick the solution to this so you can see what the answer should look like. So my answers, this is exam 4, look like this. I hope this isn't one where I made a mistake on the answers, but like you just put the answer here, converts absolutely, or diverge, or whatever. Okay, so diverge, this one was just K-term, this one's P-series, and then direct comparison. I specified direct comparison, but you did not have to on a test. You could just say comparison, and it's one of the two. And so like down here, this is like what we're doing now. So converges absolutely, P-series, limit comparison, and absolute convergence theorem. Does that make sense to everybody? So this is all you had to write, but if you did write more, that was okay. And then down here, like this is the ones like what we're doing now. This one was alternating. So we had the compare to, consider this, I'm sorry, consider this, compare that to this, and then, okay, this converged, and then this would have been the one on the far left. I just didn't put it in columns. So since the absolute value converged, the series converged absolutely by absolute convergence. This is just like what we're doing now, except it was geometric when we got over here. Does that make sense? Any questions? Okay, so let's do a few like this, not like this, like the ones up here where you're only listening to the test. I'm going to put 3 or 4, maybe 6 on the screen. And then once we're done with these, we're actually going to be done for today. So let's do this. Resume share. There we go. All right, there we go. All right, so on these problems, just give the conclusion. Like converge absolutely, converge conditionally, or diverge, and list the tests. All right, so we're going to put a few up, and I'm going to give you a couple minutes to try them, and then we're going to be done for today. But let's put these up, and you guys take a couple minutes to figure them out. Oh, we'll make that not 0. My bad. Make that 4. All right, so these 6, I'm going to give you about 2 minutes just so the video doesn't drag forever. 2 minutes to think about these. List a conclusion and the test that you would use. You don't need to list the details, but what might help is to like jot down what this is going to be. If you can do that in your head, great. If not, no big deal. But writing this far right one, that's what determines everything. And so we'll give you 2 minutes from now to try them, and then we'll work them together. All right, so I want to start working these. And then I have a few things I want to just kind of give you heads up about and talk. So just if you can hang tight for a little bit, or if you're watching this later, that's fine. Just that's why there's a few extra minutes. But okay, if you look at this, the relevant series is you're going to get k over the cube root of k to the 12th, which is k to the 4th. And so that's 1 over k to the 3rd. So you don't have to write that, but that's kind of like you're going to take the absolute value for the middle one, but the one on the right is going to be 1 over k to the 3rd. What that means is the one on the far right is going to be p series, and the conclusion is going to be that it converges. Then you're going to have a comparison test for the absolute value one. That's the one in the middle. It's going to converge. And so then the original series is going to converge absolutely. And the rationale for that one, the one that was on the far right left, the like up here when we're doing the 3 columns, the rationale for the one over here, converge absolutely, is the absolute convergence theorem. And the conclusion for that is it also converges. Does that make sense to everybody, how we're getting that? That's kind of the big deal from this whole week, is to be able to kind of come up with this.
So for the limit comparison, can we just write comparison like that?
Yeah. So when you're doing the ones where I don't want you to show the details, you do not need to make the determination as to whether it's limit or direct comparison, because that doesn't change the structure of the proof. You get what I mean?
Okay.
Okay. Like now, if you're going up here and doing it, you obviously have to show the limit comparison. And if you want to use the direct comparison, you got to show that. But when you're doing these where you list it, I don't care if you make the distinction whether it's limit or direct comparison, because
Okay.
I'm not making you show the details. That you're good. Does that make sense?
Yep.
Everybody good? Okay. All right. And so then this one, you're again going to take the absolute value. You're going to compare it to 1 over the square root of k, which is 1 over k to the half. That means you're going to have a p series, which diverges. you're going to have a comparison test, and the middle one will diverge. So if you look at this, the ones that are 3 columns, the one on the far right, P series diverges. The one in the middle, the absolute value, is a comparison test diverges. The one on the left is going to be the alternating series test, and it's going to converge because this wasn't the K-term test. So it converges conditionally. And again, I've not started writing the WebAssign part of the test, but what I'm kind of envisioning is that you will have a choice over here: converge absolutely, converge conditionally, diverge. You click the one you want, and then it'll probably be like, okay, here are all the different tests, which ones apply. And so you would check P series, you would check comparison test, you would check absolute convergence theorem for this one, you would check P series, you would check comparison test, you would check alternating series test, but not check the others for this one. Does that make sense to everybody? I think that's how that will work on WebAssign. But I haven't done that yet. All right. So number 3, when we get over here, we get K over the cube root of K to the 6th, which is K squared. And so that's 1 over K. So then you have either harmonic or P series. You could say either one, or you could say both, and it diverges. You would have a comparison test, and that would diverge. And then the original is going to be, again, alternating series test, which converges, and it converges conditionally. And man, I meant for that to be a K-term test, but that's all right. How could I have changed that so that it would have been a K-term test, which was the intent? So like if this had been K squared, it would have been K-term test and diverge. Does everybody see why? That's good. All right.
That'd be K squared over K squared, wouldn't it?
Right, which is why it would then be K-term test, because the limit of the sequence would not be 0. Because like when you get over here, it's K squared over K squared. So then you just go with the K-term test. Okay. Like the third example that we did up here, like K over K, if you got over here, would be that. All right. So then this one, you would get over here and it'd be 4 to the K over 5 to the K. Which is 4/5 to the K. That is not a P series, it's geometric and converges. You would have a comparison test. So same structure as the ones up here, except geometric here, converges. Either direct or limit comparison here, converges. That means the one on the left, the original, converges absolutely. And it'd be the absolute convergence theorem. Everybody clear? Okay, so then number 5, if you got over here, you'd get to 3 to the 4K plus 1 over 9 to the 2K minus 1. That simplifies to 3 to the first over 9 to the negative 1 times 81 over 81 to the K. That means this is K-term test because that's 1. And this diverges. Does that make sense? Okay, on the last one, make sure it's clear if you guys are trying to copy stuff down. All right, on the last one, you would get over to the far right and be 1 over square root of K, which is 1 over K to the half. That's a P series that diverges. A comparison test would show that that series diverges. This one, however, is not alternating. So that's it. This series is just a comparison and a P series. And so this diverges. It's real important to notice that because on Monday and Tuesday of this week, we were working on ones like this. And so on like the series 3 packet, you have ones like this that are not alternating. And so basically what happened with those is you had something like just this middle series. So you'd have the comparison that would converge and then the middle one would converge. Or this one, the comparison diverged and then this one diverged. We didn't have this part. That's because it wasn't alternating. The reason I say that is because once you get good at doing these alternating ones, it's almost natural to just kind of jump back and say, okay, well, then it converges conditionally by the alternating series test, which is true on problem 2, but not true on problem 6 because it's not actually alternating. And if you back up and think about that, we know that's true, but it's easy to just kind of get in this routine where, okay, you always have 3 of them. Well, you don't have 3 of them if it's not alternating, or normally you don't. All right, any questions on this set, on these 6? This is like kind of the 6 that were on that test. There were a couple other things mixed in there, and we'll have some other stuff too. I think there were more of these that weren't alternating. There were less alternating. I just wanted to do a bunch of these because that's kind of what we're on right now. Any questions so far? You guys good? Okay, so let's talk about what's coming up. So for homework, Series 3 and Series 4 are due, I believe, Monday night. Double check my email. But Series 4, it's numbers 1 to 10 that you should work on. You should not work ahead, okay? The ones after that are using tests that we've not covered yet. So like number 11 kind of looks like what we've done, but it's actually not. Because it mixes an exponential with a power function. So don't work ahead on Series 4 unless you've studied this before, but we've not gotten to those yet. So Series 4, you should do problems 1 through 10. Series 3, I think it's the first 29. It's whatever I told you guys before. And am I right? The due date is Monday night, right? I think it's Monday night
Yes.
at midnight. Yeah, okay, just wanted to make sure. So Series 3 and Series 4, Monday night at midnight. You guys have solutions to all these, so I'm kind of trusting you to make sure you can genuinely do the problems, because if you can't, the test is going to be real tough. It might also be smart to look at some old exams. Depending on the semester, this may have been covered on exam 3 or exam 4, just depending on the pacing that semester. Then I wanted to show you this handout, which is in the shared drive. So under unit 3, it's the series test summary. So this is the file name. This is structured the way that we think about it. And because your guys' test is open book, open note, you are welcome to print this out or copy this down and use it on an exam. Normally, we would not allow this handout on an exam, but the very bottom is ratio root test and integral test, which we're going to get to next week. Those, and well, 2 of those tend to be easier than these, but this handout is structured kind of in those 3 parts. So you have the basic series that would be on the far right, like either the P series or the geometric series. And then the middle part is the absolute value, but might be the original problem if we were talking about the ones on Series 3, where you're using one of the comparison tests, the direct comparison or limit comparison. And then the bottom is talking about, okay, first you test the absolute value. So you can use absolute convergence if it converges. Otherwise, you lose, or you use the alternating series test to show that it converges. But on the problems we're doing, we're probably only going to be using this on ones that converge conditionally. It technically applies to all of them. So this is the one on the far left. This is the one in the middle. This is the one on the far right, unless it's K-term test, which kind of goes over top of all of this. So the limit of the sequence is not 0, then the series diverges. Or if the limit of the absolute value is not 0, which is the way we're using it today. If the limit of the absolute value is not 0, then it diverges. So this is I think, a good summary of this. It's handwritten because I wanted it formatted exactly this way. I didn't want to mess with trying to get this into Word this way. The thing I do think is a little bit misleading is it looks like if it converges, you should use this. If it diverges, you should use this. That is not true. If it converges, sometimes you use this, sometimes you use this. If the comparison series diverges, sometimes you use these, and this is a description on how to know. But like somebody was asking earlier, a lot of times here, you can just always default to limit comparison. There are some cases where you can't, but for the most part, you can default to limit comparison test. Next week, we will get into the ratio and root test and the integral test, but I do want to talk about the schedule. Any questions about this handout? I made it because I think it's very useful. You study and you work things the way you feel like it is, or is helpful to you. If you want to restructure this in any way, that's completely fine. I won't be offended, but I do think this will help you a lot. All right, any questions so far? Okay. And so then as far as next week, so I am out of town starting tomorrow through Tuesday. So I'll be back Wednesday. I'll be back Tuesday night, but I'll be back Wednesday. I will kind of purposely not have access to email. You should take a weekend like that yourself. It's worth it. So for Monday, we will not have live lecture. So no live lecture Monday, but there are 2 videos because Monday's technically on the calendar. There are 2 videos and they're short. I just posted them on improper integrals. And I'm actually going to show you where they are. I think one's like 20 minutes and one's like 10 minutes. So it's less than what we would normally spend in class Monday. So you should watch those. So 2 improper integral videos. They are on the playlist. I had it on my browser. Let's see if I still do. Yeah. This is unit 1. So, okay, give me 1 sec. So if you go into the YouTube channel that we are using and you go into fall 2020 lecture videos after exam 2 until exam 3 full playlist, at the bottom, it's unit 1 video 22 and unit 1 video 23. So 22 is 21 minutes and the other one's 10 minutes, 38 seconds. So that's going to take you 32, 33 minutes if you don't pause or anything. I would recommend pausing, but that's taking the place of class Monday. If you'd rather get it out of the way tomorrow and not have to deal with anything Monday because the university is closed Tuesday, that's completely fine. However you want to pace it. There is a handout on improper integrals that you should look at before the exam. And that handout is in our shared drive. So if you go into the shared drive, the improper integrals part is in unit 1 and it's folder 8. And there's an improper integrals handout with some problems. And then there's solutions to those problems. There's actually just the answers to those problems. I'm not collecting those at all, but you should do them kind of just to prepare for the exam that we have in a couple of weeks. So the improper integrals, that's the topic for either tomorrow or Monday, however you want to pace it. It was on the calendar with the test a couple of weeks ago, so you may have already done this. And if you have, great, then you're off tomorrow and Monday. But that is it for me for the week. If you have questions, stick around. I'm happy to answer them. If not, you guys have a really good weekend, and then we will be back to live lectures on Wednesday. So no assignment at all for Tuesday. The university's closed. You should vote if you have not. But other than that, we are good. Have a good weekend, and I will see you guys next week.